Hi everyone. In this lesson, we're going to discuss how to limit the width of a confidence interval. So when constructing a confidence interval, keep in mind that there are times when we would like to limit the width of that confidence interval so that we can state that our point estimate is within a specified distance from the true population mean or proportion with a specified degree of confidence. So for example, if we have a point estimate of 10, let's say, so x bar is 10 for some unknown mean, and our 95% confidence interval, say, is 8 to 12, then we can state that our point estimate of 10 is within 2 of the actual mean with a confidence level of 95%. Now notice that the width of the interval here is 4, but we state that the point estimate is within 2 units of the actual mean because 10 is right in the middle of the interval. Notice this graphic down here. So if this is our interval from 8 out to 12, and our mean, if our mean lies in here somewhere, say it's right here, then notice the distance from our point estimate of 10 out to the mean is less than 2, 2 being half of the width of this interval. So we can state that our point estimate 10 is within 2 units of the mean with a confidence level of 95%. Remember that 95% means that once we constructed this interval, there is a 95% chance that the true population mean lies in here. There is still a chance that it could actually be outside the interval somewhere. Now in the next slide, we'll show how we can limit the width of our confidence intervals in certain cases. And we can do that by choosing appropriate sample sizes n. So we'll take a look at that now. Now in the first case we're going to look at where we can limit the width of our confidence intervals, that's going to be in case 1 that we studied previously for confidence intervals where the population standard deviation sigma is known. So consider the confidence interval discussion from case 1 where we studied where sigma is assumed to be known, and recall that this was our formula for a confidence interval when sigma was known. This is a confidence interval for the mean, remember. Now this quantity right here in our confidence interval, this piece right here, that's our margin of error. That determines the width of our confidence interval. You see, twice this number is the width of our confidence interval. So if we want to limit the width of our confidence interval, which is determined by this value e right here, what we can do is take this equation right here, specify what we want e to be. Remember, e is half the width of our confidence interval, and then we can solve this for n. And when we take this equation right here and solve for n, this is what we get down here. It's just a little bit of algebra. Multiply the square root over to the other side, divide the e over to the other side. I'll just show you here what you would get in that case would be the square root of n would be that's what you would get when you would take the square root of n over to this side by multiplying and dividing e to the other side, and then you have to square both sides to get rid of that square root, and you end up with this right here. So if we specify what e should be, then that tells us what sample size n we should choose. All right, so there's a formula for case 1 where sigma is known, and this will tell us how large our sample size would be so that we limit the width of our confidence interval. Now let's take a look at this example where we determine a necessary sample size when the population standard deviation sigma is known. So a student in public administration wants to determine the mean amount members of city councils in large cities earn per month as compensation for being a council member. The error in estimating the mean is to be less than $50 with a 90% level of confidence. The student also found a report by the Department of Labor that estimated the standard deviation to be $1,000. What is the required sample size that the student should use? Now in this case, our error E is going to be the $50. So that's our error E right here. The population standard deviation is 1,000. That came from a previous study. So we assume that the population standard deviation is known to be 1,000. Now the significance level in this case is 0.1, which is 1 minus your confidence level. Your confidence level is 0.9, coming from the 90%. So that's our significance level, 0.1, 1 minus 0.9. And the Z alpha over 2 that we want to use in this case is 1.645. That corresponds to a significance level of 0.1. You can look that up in a table, or if you want to use Excel, remember you can just type in this command right here, norm.inverse 0.1 over 2, 0, 1, and that'll give you back 1.645. So now we can calculate our necessary sample size right here using this formula. So we just plug in what we have for the Z alpha over 2, the sigma, and the error E that we desire. So we get 1.645 times 1,000 divided by 50. We square that, and we get 1082.41. And it's convention to round that up to 1083 in this case. Note that usually you'll see these numbers rounded up because we want to determine a minimal sample size. So by rounding it up, we're playing it a little bit safer than if we round it down. So the student should use a sample size of 1083 so they can state that their point estimate or sample mean is within $50 of the actual mean with a confidence level of 90%. Let's take a look at one more example. So here a consumer group would like to estimate the mean monthly electricity charge for a single-family house in July within $5 and using a 99% level of confidence. Based on similar studies, we can assume the standard deviation is $20. How large a sample is required? So for this problem, our error E is the $5 that we want to be within. The alpha in this case is 0.01. That comes from the 99%, so that's 1 minus 0.99. The Z alpha over 2, in the case of a 0.01 significance level, is 2.576. You can look that up in the table that we saw previously, or you can use Excel to calculate this. Just like we did previously, you would just type in norm.inverse. And you would use 0.01 over 2 as your first parameter, 0, 1. Type this into Excel and you'll see that you get back 2.576, so that's our Z alpha over 2. Our sigma is 20, and so this is our necessary sample size right here. Z alpha over 2 times sigma, divided by the error E that we want, squared. And when you evaluate this, you'll see that you get 106.17 and round that up to 107. So that's the sample size that should be used to state that your point estimate is within $5 of the actual mean with a 99% level of confidence. Now we're going to take a look at how to determine necessary sample sizes for population proportion problems. So for a population proportion or percent problem, we use these two formulas here to estimate the necessary sample size needed to state that our point estimate is within a certain error E from the true population proportion P with a specified confidence level. So for the first formula that we have here, 0.25 times Z alpha over 2 divided by E squared, we use this formula when we're given no information about the population proportion P. So if we have no idea what the population proportion is, or a decent estimate for it, we use this formula. Now the second formula here we use if we have a good estimate P hat to the true population proportion P. So maybe this P hat came from a prior study and we have a feeling that the true population proportion hasn't changed much. In that case, we can use this formula here. Now for both of these formulas, the Z alpha over 2, that is determined from the significance level alpha, just like we've done before, and E is the specified maximum error that's desired. Now this is going to be a number between 0 and 1. If the problem states it as a percent, then you're going to have to convert it into a proportion by dividing by 100. Now we'll verify these equations later, but let's just take a look at a few examples first of how we use them. Now in this example, the American Kennel Club wants to estimate the percent of households that have a dog as a pet. Now the club wants their estimate to be within 3% of the true population percent. So the question is, how many households should they survey? And that is assuming a 95% level of confidence is desired. Now for our solution, note that the maximum error E is stated to be 3%. But we need to convert that to a proportion, so we divide this by 100, and we get 0.03. So this is the value that we'll use in our formula. Now our desired confidence level is 95%, so the significance level alpha will be 0.05, that's 1 minus 0.95, and the corresponding critical value Z alpha over 2 will be 1.96. You can verify this using the norm.inverse function in Excel with a significance level of 0.05, as we've done before. Now note that there's nothing in the problem that indicates that we have a good estimate P hat for the true population proportion P, so therefore we use the formula with the 0.25 in it. So this is the formula that we want to use for N, the sample size, and we just plug in what our Z alpha over 2 is, what our desired maximum error E is. Here we have it over here, so 0.25 times 1.96 divided by 0.03 squared. Notice we use 0.03 here, don't use the 3%. And when you evaluate this, you'll get 1067.11, and you should round that up to 1068. So that is the minimal sample size that they should use. Now let's take a look at another problem. Now in this example, a researcher wants to estimate the proportion of cities that exclusively use private refuse collectors to collect their waste. The researcher wants the margin of error to be within 0.05 of the true population proportion, and the desired level of confidence is 90%. Now from an earlier study done 5 years ago, the proportion was found to be 0.23. Now let's answer these two questions. Assuming the proportion has not changed significantly, estimate the required sample size. And part B, assuming the previously found proportion is no longer accurate, estimate the required sample size. Now notice in the problem up here we have this 0.05 and 0.23. Keep in mind that sometimes you'll see these stated as 5% and 23% if the problem is stating percents instead of proportions. Now if you are given percents, you do need to convert them into proportions by dividing by 100. So keep that in mind when you're working through your homework problems. Now let's take a look at the answers. So for this problem, let's note that our maximum error E that we want is 0.05. Our significance level is 1 minus 0.9. This comes from the 90%, and that's going to be 0.1. So that's our significance level. In which case then the Z alpha over 2 is going to be 1.645. So remember that from our table, or you can use the Excel command that we have written here. Now to answer part A, assuming that 0.23 is relatively close to the true population proportion, we can then use this estimate here that has the p hats in it. So this is going to be our p hat, the 0.23. So we put 0.23 in here and here. Our Z alpha over 2 is 1.645. The E is 0.05. And this is what we get right here. Evaluating this on your calculator, you'll get 191.69. And we would round that up to 192. So that's the necessary sample size that the researcher would need, 192 or more. Now for part B, assuming that the 0.23 is not a good estimate anymore, in that case then we have to use this as our estimate for the sample size, the formula with the 0.25 in it. So we put the 1.645 in for the Z alpha over 2, our critical value. E is 0.05. This is what we get right here. Evaluate this on your calculator, and you'll find that you get 270.6, and you would round that up to 271. So that's the necessary sample size if you assume that you have no information about the true population proportion. Notice that this number is bigger than 192, which makes sense because in part A we're assuming that we know something about the true population proportion that is close to 0.23, whereas down here we're assuming nothing about the overall population, so we need a larger sample size.